The adult human body contains 206 bones at maturity. This entire assembly functions as an engineered mechanical lever system. In this musculoskeletal system, anatomical form rigorously dictates mechanical function. The physical shape of a biological component determines exactly how it behaves under physical stress. Understanding human biomechanics requires an analysis of three distinct structural layers. The first layer consists of the rigid levers themselves, the geometric classification of the bones. The second layer involves the fibrous connective tissues that link these individual levers into a continuous chain. The third layer is defined by the precise kinematic constraints of synovial joints, the junctions where movement is permitted. Mapping this three-part taxonomy allows us to predict the exact mechanical behavior and limitations of any structural joint in the body. The 206 bones of the skeleton are divided into 5 distinct categories. This classification is based on their macroscopic geometric shape rather than their overall size. The first category is long bones. These are cylindrical structures that are strictly longer than they are wide. Looking at this stylized matrix mapping bone classifications, we see the long bone category. These act as primary levers, moving when muscles contract. The femur in the leg and the phalanges in the fingers utilize this cylindrical geometry to maximize mechanical advantage. Next are short bones, characterized by a cube-like structure. Their length, width, and thickness are roughly equal. Because they lack the length to act as significant levers, short bones provide localized stability and controlled, limited motion. These are found in the carpals of the wrists and the tarsals of the ankles. The third category is flat bones. While these structures are typically thin, they are often curved like the sternum or the cranial bones. This geometry provides broad surface areas for muscle attachment and serves as a physical shield for underlying internal organs. These 3 primary bone shapes demonstrate a direct structural trade-off. The geometry shifts depending on whether the local anatomical region must maximize leverage or prioritize protection. The final 2 classifications handle specialized localized stresses. Irregular bones are those with complex shapes that do not fit the previous geometric categories. The vertebrae are irregular bones. Their multifaceted geometry allows them to bear multidirectional compressive forces while shielding the spinal cord. Finally, we have sesamoid bones. This schematic illustrates a small, round bone forming directly inside the fibrous sheath of a tendon. They protect tendons from mechanical wear, helping them overcome extreme compressive forces at high-pressure joints. The patella is the primary example. Irregular and sesamoid bones illustrate how the body departs from standard geometry when localized mechanical stresses require a custom structural solution. Regardless of their shape, rigid levers are static. A bone cannot move or stabilize itself in isolation. Moving this frame requires fibrous connective tissues to bridge the gaps between levers. Ligaments are defined by their anchoring points. They attach bone to bone. The function of a ligament is structural stability. They prevent abnormal, out-of-bounds movement at a joint. Tendons, by contrast, attach muscle to bone. A tendon's function is kinetic. It transfers the mechanical force generated by a contracting muscle directly into the bone lever. The system operates as a binary. Tendons actuate the levers, while ligaments restrict the framework from mechanical failure. Synovial joints are the specific anatomical junctions where these bones meet and articulate. The complexity of any joint is determined by the number of articulating surfaces involved. Joints are categorized as simple, complex, or compound based on these contact points. Joint mobility is quantified through degrees of freedom. As shown in this diagram, degrees of freedom refer to the specific number of axes a joint can rotate around. Uniaxial joints have only 1 degree of freedom, locking rotation to a single axis. Biaxial joints have few degrees of freedom, allowing movement across 2 axes within a dimensional plane. Multiaxial joints possess 3 degrees of freedom, granting the lever full rotation across all spatial planes. Calculating a joint's exact degree of freedom mathematically defines the absolute kinematic limits of that specific anatomical junction. A joint's degree of freedom is dictated entirely by the physical 3D shape of the opposing bone surfaces. Plane joints feature nearly flat opposing surfaces, allowing for uniaxial gliding movements, such as those between the intercarpal bones of the hand. Hinge joints match a concave surface to a convex one. This mating geometry restricts motion to a uniaxial degree of freedom, seen in the bending of the elbow. Pivot joints also operate on a single axis, but they are engineered for uniaxial rotation, such as the atlantoaxial joint that allows the head to turn. Ellipsoidal joints fit an oval convex shape into an oval concave surface. This creates a biaxial joint with 2 degrees of freedom, like the wrist. Saddle joints feature interlocking saddle-shaped surfaces. This specialized geometry permits multi-axial movement across multiple planes, as seen at the base of the thumb. Ball and socket joints insert a spherical head into a concave cup. This design provides 3 degrees of freedom, allowing the wide, multi-axial rotation of the shoulder and hip. These physical mating geometries block off specific planes of motion. The joint will only articulate exactly as its bone shapes allow. When we observe a complex, full-body movement like an athletic throw, we are watching this entire taxonomy fire in unison. The movement originates as muscle force is transferred into the skeletal system through the tendons. That force pulls against long bones, utilizing their cylindrical geometry as primary levers to multiply the speed and power of the action. The exact trajectory of that lever is governed by the mating geometry of the synovial joint, while ligaments hold the structure intact under the sudden mechanical load. Human movement is the predictable outcome of rigid bone shapes, specific connective tissues, and joint geometries operating in synchronized unison.